frameworks or any difficulty people were having with any of the p-value, critical value? So the p-value is always the probability in the tail of the test. Okay, so you're going to go ahead, you're going to compute your test statistic, your t-score, your z-score from the data, and then you just always take the area of the tail. Except when it's a two-tail test, and you have to multiply it by 2. Okay. The p-values and probabilities and tails. Okay. Other questions? Other things we want to address? Okay. So what I want to do today is talk about two-sample t-tests. We introduced, we were talking about, one-sample hypothesis test. What a one-sample hypothesis test means is that you're looking at one sample and you're comparing the mean of that one sample to some sort of fixed value, right? That's what we did. And we talked about two cases. We talked about when the population standard deviation is known, and then we said we'll use z-scores, right? And we talked about when it wasn't known, and we said we had to use a t-distribution. Now, what happens when we have two samples? So this is kind of a different problem, all right? So this is a situation that happens a lot, but we want to compare two different populations. We don't have either one. All we have is samples from the two. What can we say? And it turns out there's two flavors of this test. One's called a paired and one's called an unpaired. And we're going to discuss what that means. So one of the questions you're going to have to think about when you're doing these two sample tests is, which am I looking at, paired or unpaired? Now, the really cool thing is that when we actually do these tests, they're really easy to do in Stack Crunch. So, you just ask the question of like, what is the p-value, what is the critical value and everything. For one sample, you had to kind of grind through all those details. It turns out that for two sample, the details are gory enough that we don't even bother grinding through them. We just have Stack Crunch take us right from the hypothesis, right to the p-value. So easy peasy. Okay. So what is an unpaired test? So here's kind of the idea. Here's where we're going with this. Let me get a better, none of these markers are working. So here's kind of the notion between an unpaired test. So with an unpaired t-test, what we're doing is we're comparing samples from two different populations, okay? So here's one population, here's another population, and we're taking little samples from them. We're computing the means from each of those samples, and we want to say something about the relationship between the population mean. So this is what we don't know. We don't know mu1, of course, and we don't know mu2. This is called an unpaired t-test because the idea is that the individuals in this sample are not the same as the individuals in this sample. They're totally different populations. So the things here do not live in here. Okay? And that's the hallmark. So the hallmark of an unpaired t-test is that the subjects in the samples are not related. And so we have some sort of hypothesis starting off. Well, what are the sorts of hypotheses we can have? Well, we can hypothesize that this unknown mean is bigger than this unknown mean, right? Or it's less, or it's not equal. So there's three types of hypothesis tests we can do if we look at the alternative. So the one is we could say that mu1 was less than mu2, or I could rewrite this like this. I could say that mu1 minus mu2 was less than 0. Then this will look a little bit more like the hypothesis test we had last time, where, remember what we had? We had an unknown parameter here, right? And we had a number here. It looks a little more like that. Or we could test that they are not equal, which again, I could kind of recast like this, right? I could bring all the mu's over to one side, and I could say this. Or finally, I could do an upper tail test. So these are the different types of hypothesis tests we can form. notice that when we're doing these tests, we have to be really careful about which sample's which, right? I mean, the order definitely matters here, okay? So we're going to have to be kind of mindful of that. So let me kind of give you an example. Let's suppose we want to ask, is the average GPA of aeronautical engineers at Embry-Riddle higher than the average GPA of electrical engineers? And so these are my two unknown populations, right? And they each have a mean GPA for aeronautical engineer and electrical engineer. And so how would I do that? Well, I would take a little sample, right? So maybe I take 4 aeronautical engineers, 5 electrical engineers. Notice that this is now an unpaired T test. The people in this sample are not the same as the people in this sample. And I know you could say, what if the devil made you? We're not going to consider that situation, all right? So there's no relationship. In other words, when this person's picked, it has no influence on who's picked here. These two samples are random with respect to each other. And so what might I want to know? Well, I might want to know, for example, is the average GPA of aeronautical engineers higher than electrical engineers, right? That would be the same as testing this. So usually double E's are considered really hard major, but here at Embry-Riddle, aeronautical engineering is probably the hardest major, so I might want to test this, right? So what would I be doing? Well, obviously, to do this test, the sample mean for the aeronautical engineer would have to be higher than electrical engineers, right? It would make no sense to test this if the evidence was the opposite, right? So first of all, we know that to run this test, the only way this makes sense is if the sample means, the difference of the sample means is positive. And so we're going to ask ourselves, okay, it's positive, but is it so positive, is it so large that that couldn't happen by random chance, right? Then this would be evidence supporting the alternative. So that's kind of where we're going with this. So any questions about what an unpaired T test is, what it is that we're doing? Everybody's good? So how do we do this in StatCrunch? Well, it's really easy. So if you want to go ahead, I asked you guys to download the data set. And let's work with the GPA data set first. And what I want you to do is go ahead and open it up. And then notice what you're going to do. You're going to go to Stat, T-Stats, just like we did for the confidence intervals, right? But now instead of one sample, you're going to choose 2 samples. Now notice what we said before. We said there's different ways of running this. Notice that you could either do it with data, if you have a data set, or you could do it with the summary statistics if you have the mean and the sample standard deviation and all that stuff. Okay? So go ahead and do that and see what you get. Nope, this is the beautiful thing. Don't worry about everything else. Just ignore it. Easy peasy. That's the word for today. Easy peasy. Well, I guess it's 2 words. That's the words for today. All right. I can't wait till we just have computers that plugged in for operations. No, actually, I can't. Yeah, I will. All right. So what you should find when you do that is a new window will open up, and so Noah. And so with data. Okay. Now notice I got to be careful. I got to be careful what the order is, right? So here's what I want to test, okay? I want to test if the GPA of aeronauticals, the average of the GPA of the aeronautical engineers, this is what I want to test. So notice that if I call this 1, and I call this 2, right? Notice what the hypothesis tests. So in other words, when you enter your samples, okay, I'm going to go ahead and I'm going to choose aeronautical engineering as being the first sample, the double E's as being the second. Notice that the format of the hypothesis test, okay? The format asks us to look at mu1 minus mu2. So 1 is aeronautical engineering, 2 is double E, right? So I'm looking at the mean of aeronauticals minus double E's. I'm testing to see if that's greater than 0, right? So this is what StatCrunch looks at in the hypothesis test. So here I'm going to choose this to be greater than 0. Okay. And that's all we have to do. Don't do anything else. You can do other plots if you want to play around. I totally encourage you to, but you don't have to, all right? And there we go. I want you to look at the output. See if you can make sense of it. Which of those quantities do you know, do you recognize? Do you recognize any of those things? Standard error. Standard error, okay. P-value. What's the most important thing to look at? What's the thing that your eye wants to go towards? For sure. What is the goal of inference? We want to draw a conclusion, right? I want to decide between two hypotheses. How do I make a decision on those two hypotheses? What do I make? So if I said you can pick one thing from this table to make a decision, what would you choose? You would choose the p-value, right? You're going to compare the p-value to alpha, okay? So here you notice this p-value is very, very small, 0.005. What was our alpha in this problem, by the way? Right, I never said so. When we don't say the default's 0.05, okay? So something to remember is that alpha only has 3 values for all practical purposes. When we don't specify it, this is the default. And so remember the rule that we use, right? The p-value, what does it represent? It's the probability the null could be true given all the information against it. So this is saying the probability the null hypothesis could be true is 0.5%. That's too small, right? So what do? We flip. We say we don't believe the null anymore, right? So our p-value here, which is equal to 0.0053, right? It's less than, and notice it doesn't really matter. I can take the smallest value of alpha. I'm still going to reject, right? So the p-value is less than alpha, so I'm going to reject the null hypothesis. And so I'm going to say at a significance level of, and I can take the very strongest level of proof at a significance level of 0.0. Whoops, sorry. I meant to say 0.01. Sorry. So the idea is the p-value is less than the smallest value of alpha, right? So I would say at a significance level of 1%, we find there is sufficient evidence to conclude the average GPA of aeronautical engineers is greater than the average GPA of electrical engineers. It's always the same thing. At a significance level of, okay, go ahead.
Can we also use sample difference?
So yeah, so we didn't get to. So that's a good point. Let's look at the other things. Okay, so this is the sample difference. What does that represent? What is that?
So it's the average we subtract mu1 minus mu2.
So, but be careful. So it's the difference of the average, but it's the what? What averages?
The averages of the GPA for each separate
sample, right? So this one is going to be x1 bar minus x2 bar, right? The standard error is basically the standard deviation of that difference. And what that is, we don't know. We haven't gone into that, okay? But here's the thing that's really important. Notice that we always take a difference, okay? This is x1 bar minus x2 bar minus the hypothesized value divided by the standard error. It gives us the test statistic. That's actually that's what they call t-stat. That's a test statistic. Okay. So here's something to kind of bear in mind, and you don't have to know this for the exam, but it's really useful, I think, if you want to understand anything about statistics. Is that we have these things, right, where we take a data value, minus the mean under the null hypothesis divided by the standard deviation. This is a really common theme, right? This is what a z-score looks like, and this is what a t-score looks like, okay? And that's what's actually going on here. This is x1 bar minus x2 bar. This is my data. The mean under the null hypothesis is 0, divided by, and we're not even going to get into what this is. If you want to know what that is, take 412. That's the upper level course I teach. This is a standard deviation of this difference, and we're not going to get into this, okay? But this is exactly what a test statistic is. It's a ratio. So here's what I want you to think about, and this is really important. Notice what a test statistic is. It's the number of standard deviations you are from the mean, right? That's what a test statistic is. So this is telling you the absolute distance. This is telling you the standard deviation. And this is telling you how many standard deviations that value is from the mean, which is 0. That's a very important concept to understand. So remember I told you guys a long time ago that when I first took statistics, I didn't really get the central limit theorem, didn't really understand it. And I said that when I did, everything about statistics instantly made sense. This is the reason why. Because 90% of the things that we study in statistics look like this. They look like the number of standard deviations from the mean. That's how we tell how extreme something is. So it's a very important concept. But all we need is the p-value. And of course, it might ask you in the question, it might say, what is a test statistic, right? And just copy and paste that, okay? But it's a good thing to know what it is. Test statistics are always the number of standard deviations, right, from the mean. Other questions we have about the printout. Okay, so here's the thing. Here's what happens in real life, though. In real life, you rarely have the data. Very, very rare that you can actually get a hold of somebody's data. So what happens? People publish a study and they give you the summary statistics, right? They say we looked at so many people, the sample mean was this, the sample standard deviation, right? So they don't give you the data. So what do? Well, turns out in StatCrunch we can solve this problem. So notice that we can also run StatCrunch. If you go back to StatCrunch, you'll notice that when you went to run this test, okay, it gave you two options, with data or with summary. With summary is talking about the summary statistics, right? Those are the numbers that kind of boil down the whole data set, right? So the summary statistics would be the sample mean and the sample standard deviation. So we can go ahead and click on that. And notice what it asks us for. These are the summary statistics. A statistic is what? Does anyone know offhand what a statistic is? You're studying statistics. What is a statistic?
A number that describes a characteristic of the population.
Yeah, and I'll put a little finer point. We'll just say it's anything we can compute from a sample. Okay, so a statistic is something we can compute from a sample, okay? So a summary statistic, now kind of going back to what you want to say, a summary statistic is something that kind of captures the main features, right? So a sample mean kind of captures where the center is. A sample standard deviation captures the width. It kind of summarizes the data set, right? So here's what we have to do. We need the sample mean, the sample standard deviation, and the sample size. So guess what? We just get that from StatCrunch. So I want it for both of these. And all I want is the sample size, the mean, and the standard deviation. That's all we need. Oops. And now you can just copy and paste those values right into the little window, right? Again, the same caveat applies. You have to be careful about the order, right? It matters which one you call 1 and which one you call 2 because you're doing a one-sided test. So here my sample size is 4. Here my sample size is 5. So my mean is here.
And you know, the thing you want to do is you want to be careful when you enter these numbers. Make sure you put the right thing in the right place. Sometimes means and standard deviations can kind of have the same magnitude. So I want to do greater than, right? And then we're going to hit compute. Do you get the same results as you did for the other one? Oh, okay. I just did summary stats. So remember how when we had a data set, right? We just went ahead and computed the mean and everything. We do summary stats column, and then you select these two, and then just the mean, the standard deviation, the sample size. Okay. All right. Yeah.
I got the right one with this one.
We did something wrong. Let's go back and see really quick.
But everything else is fine.
Can you click on the options? Let's go to edit. Okay, can you choose something? Oh, you have not equal to. So it's one tail. So yeah, you got to be careful about the direction and the type of test. Make sure if it's two sample, you have two tail test, you have two tail test. Okay. Do you know how to do it? Yes. Are you doing the same results as you did with the other one?
Yeah.
Hold on. Make sure that I had that.
Yeah, you just have to make sure that.
Make sure you're saying greater than.
And not. The p-values.
You gotta be careful of this test, right? So what am I testing? I'm going to see if the aeronautical is greater than double these, right? And so I chose the aeronautical as 1 and double these as 2. So this is going to test that the 1, which is the aeronautical engineers, are greater. But notice if I flip them, if I put the double these first and aeronautical second, flip the direction, right? And notice that when you run this, you should get the same result.
Oh, the sample size, yeah.
Okay? You should get exactly the same result. So questions on unpaired T test? Everybody's good at that? Now, let's look at paired T tests. Paired T tests are the more interesting things. They're actually, they're the sorts of things that you see a lot when people are talking about medical trials and stuff like that. So here's the basic idea behind a paired T test. So the idea behind a paired T test is that we have one population where we're looking at the same sample under two different conditions, okay? Very different than unpaired, right? So unpaired, we start off with two different populations. In a paired T test, the idea is that we only have one population. We take one sample and we test it under two different conditions. And of course, you know, what are we doing? Well, we're measuring something. We're measuring some quantitative variable, right? So this is the mean of this sample under condition 1, the mean of this sample under condition 2. This is why it's called paired. These are the same things, right? They're just under different conditions. So medical trials are like this, right? When you want to see if, you know, some drug cures headache, what do? You measure the pain level of someone before they take the drug, right? Have them take the drug, measure that, something like that. So here's one we're going to look at. We're going to look at a hypothesis test where we look at some textbooks, and we want to look at the price of the textbook, the average price on Amazon, and the average price in the bookstore. And of course, what test would you think to run? You would think that the average at Amazon is lower than the bookstore, right? So this is why I would be testing. But the mean price in Amazon minus the mean price in the bookstore is less than 0. So now I'm doing a lower tail test. I'm not doing an upper tail test, right? So let's go ahead and download that into StatCrunch and play with that a little bit. And notice that it's actually very similar, right? It's going to be stats, t-stats, but now instead of two sample, you're going to go to paired. Whoops. And you go to textbooks. So you go to stats, t-stats, and then you choose paired. It's also a two-sample t-test, but they give it a special name. Okay. And click on that. And notice that it's exactly the same. The format of how you enter the things is exactly the same, right? I'm going to click on my first variable, click on my second variable, make sure I set up my hypothesis test the right way. Notice here it's a little bit different. So we don't really use mu1 and mu2. We use mu_d. That's the mean of the difference. Okay. So here's how we think about the data sets, and you don't have to write this down, but here's kind of the idea. What's actually going on is this. So just continue this down here, okay? So this is the first sample under the first condition, the second person under the first condition, the third person under the first condition, right? The nth person under the first condition. And then the same thing, the first person under the second person under the second, third person under the second, nth person under the second, right? Now here's what we do. We actually look at the difference, okay? So this is equal to D1. We look at the difference. D2. Okay. This is a minus sign, okay? D3, Dn. And we actually study these. Okay, so this is what we're analyzing right here. So ud is equal to the mean of all the differences. It's the mean of the differences. Okay? And I don't want to get into that, but it's just kind of good that you understand what that means, all right? Okay, so let's go ahead and run it and see what we get. Amazon, bookstore. Let's see, I chose greater than last time, so I should choose greater than this time, right? And I'll get this. Okay. Is that what everybody's getting? No. What did you get? I should do last thing. So the moral of the story is that be mindful about what you're doing, okay? And it's easy to get turned around. If you got this on a quiz or on an exam, how would you know that this is probably wrong? Okay, that could be one way. But no, actually the mean's the mean. This is actually Amazon minus the bookstore. That part's negative. That wouldn't throw me off. What is it that would throw me off? A p-value. So when you get a p-value above 0.5, something happened. Either one or two things happened. Either you made a mistake, you did the wrong direction, or it's a stupid test. Okay? Meaning that you're testing to see if something is less than, and the evidence is exactly the opposite. The sample means greater than. Okay? One of those two things. That's what would clue me into that. But in this case, I just entered it wrong. On purpose. Okay. So now I'm going to change it, do it the right way. And that looks more like it. Okay. So again, p-value really small, smaller than any alpha I could use, I'm going to reject, right? Now here's kind of a cool question. What if I wanted to make a confidence interval? What if, for example, the bookstore said, you know what? That's fake news. That's fake statistics. Because this is just one value, and you know, by the way, this is a valid criticism. You're just using a single value, but there's really a spread around that value, and we don't know how big that spread is. And that's a very valid criticism. What could we do? We could construct a confidence interval, right? A confidence interval for what we think the difference of those two means should be. How do we do that? Same command you just used. So here, check this out. This is the hack. Click on Options. And now, instead of Hypothesis Test, just click confidence interval and set the confidence. Okay? And go ahead and run that. What level of confidence do you want? 95 is so boring. 99, there you go. So 99 would, so, and here's the thing, if you wanted to counter the bookstore's argument, what would you use? Would you use a 90% confidence interval or a 99% confidence interval? Right, if you're Amazon and you really believe you're less, you're going to make it as big as possible, right? You're going to say, I'm 99% sure the difference lies in this interval, right? Okay.
On the test, will it tell us to select that, like what level to put, or is that up to us?
Right, so you always have to be given either, so if you're doing a hypothesis test, you have to give an alpha. If you're not, you assume it's 0.05. Same with the confidence, you have to be given the confidence. If it's not given, you assume it's 0.95.
Okay. Got it, thank you.
Okay. Okay. So the relevant part of this table is the upper and lower limits, right? So this is the confidence interval. It says that what this says is that the true difference in the means, the mean text price, is between minus $46 and roughly minus $3. So what this tells us is that we are 99% confident that the difference in the means is between minus, roughly $46 and minus $3. Okay. And that would refute the bookstore. Yeah.
So, if the upper limit was positive, would that mean that the bookstore or Amazon isn't always cheaper?
So here's the point. That range is telling us all the possible values that the difference in the mean could be. So if 0 or a positive number was in there, then the average actually could be positive, right? Even if the majority of the confidence intervals are below, they're all possible means. We don't know which one's right, which one's wrong. So then the bookstore would say, you don't have good evidence. And if I had made the confidence a little bit bigger, if I was too confident and made it like 0.999, so I'll just show you really quick. So suppose I'm Amazon and I'm a little too cocky and I say 0.999, you notice that now it contains a positive number. Okay? And still the bookstore can say, well, there's a 1% chance your interval did. They can still say that, right? But if you're the consumer, what are you going to go with? The 99% or the 1%? You're going to go with the 99%, right? Okay, good questions. Any other questions we have about two-sample T tests? That's pretty much all there is, really. So here's what I want to do. Why don't we take a break? And I have some practice problems on my stat lab if you want to check them out. And I hope you do because we're going to work on it after the break. And let's see. Yeah, it's called inference with two samples. See that guy there? We'll go ahead and work on those when we come back. I'm going to start the roll off with you when we come back. Okay, we'll take a little, what time is it now? We'll take a 5-minute break. How's that?
I mean, that is very true. You can also live up to 50 years old after cancer was over. It's very, but you could also die from cancer. If you start to smoke. And cancer.
Ridiculously.
By the way, keep me in the loop when you need new stuff. Okay, so just let me know. Okay.
I was just checking there on Canvas, and I saw like the missing stuff.
Okay.
Obviously, I've got a lot of it here. I gave you them. I gave you the binomial and the normal homework the other day.
Yeah.
But the one thing I was wondering was like, I know I've done some quizzes in that class, but like none of the quizzes or exam 2 have a grade yet.
Let me look and see. I know the last ones you gave me. I'm gonna do this weekend. I've just been.
Yeah, I mean it's like that. Yeah,
and I don't worry about you a great deal.
Panicked there. I was thinking, wait a second about. Because I
I
did
know.
give you the exam 2, didn't I?
Yeah.
I was just like, yeah, I've been worrying myself thinking I haven't handed anything. So.
Yeah, I don't want to freak you out. No, you're fine.
That's good.
So how are the other classes going? Yeah.
That's really rude.
Oh well, this is alright. 442 is a bit of a nightmare. It's a bit like it's a bit over my head.
That's Professor Drion, right?
No, that's Mankin.
Oh, yeah. He's hard.
That's a nightmare. And then there's like I picked this computing class, but it turned out there was a prerequisite, and I've never done any kind of computing before. So that's also a nightmare. I don't know. I'm trying my best.
But it's good to see the applications. The problem I made as a student, I made the mistake that I studied all theory, and then which helped me because I was really good at the theoretical stuff. Which it's always easier to go down, But then you still got to pick up the computational stuff too. So.
Yes.
Is this
I said no, I'm smart one.
Is this like the Theorem smart T Test? Is that what I'm going to be using for
No, actually, you're doing regression.
I meant to send you the
Okay. Yeah, let me know.
I'm going into grad school.
Okay, so why don't we get back into it? Point is proving. So, the first problem is a really good problem. It really kind of tests your abilities here. Unfortunately, I made it the first one, but I want you to kind of puzzle through it and see what you think. How would we approach this? It helps to open up the data set by the way. I think the data set kind of gives you some clues as to what to do maybe. Okay, there's a data set down here. Okay. And we can open it up in StatCrunch, right? That is a really good question. We have to decide between paired or unpaired. How do we know?
I think it's paired because you're testing the same thing, but with two variables like women and men.
How many people agree? How many people think it's up? So here's the one argument. The one argument for paired is that the things that are the same are the machines, right? So we're looking at the machines under two different conditions. One is where the men use them, right? And the other is where the women use them. So this would argue that this is paired. Does anybody agree, disagree? There is another interpretation that you're looking at the difference between men and women. Those would be two different populations, right? That would be unpaired. So which one is it? Are we looking at the same thing under two conditions, or are we looking at two different populations? It's a hard question, actually. What do you think? The data set kind of tells you, right? So the data set, if you look at the data set, the data set kind of shows you that this is going to be a paired T test. Because notice that I'm looking at the same thing. I'm looking at treadmill, right? Under really 4 different conditions. It's the same thing, but under 4 different conditions, okay? So it's actually a paired T test. And that's tricky. Because what would you naturally think? We naturally think of people testing humans, right? We don't think of people testing machines. And we don't think that there should be a difference if 2 different people use the same machine. But that's not what the problem is saying. So this is going to be a paired T test. So how are we going to do this? Well, it asks us for a confidence interval, right? So it wants to know the 95% confidence interval. How should I set this up? Let's go into StatCrunch and take a look. So whenever we're doing anything paired, whether we're doing a hypothesis test or a confidence interval, right? I always use the same command. Stat, T-stats paired, okay? Now let me ask you a question. What order should I enter them? The question asks me how much longer, and I'm looking at the time it takes for them to burn 200 calories, right? So it's asking me how much longer it takes women than men. So who should come first, women or men? Women should come first, right? So I'm going to look at women. And I also got to be careful too, because notice that there's 2 different conditions that the people are working under, light and hard, right? So it's the women working under light, strenuous exercise, and the men working under light. And it wants what, a 95% confidence interval? And that's how we get it, okay? Is everybody good on this? Is it working out? Yes? Okay. So go ahead and enter your answer. See if that works for you. Let's see, it's 3.29, which is 3.3. 16.7. Notice that if you enter them the wrong way, you'll get the wrong answer. You'll get negatives, right? The stack crunch will or my stat lab come off of them. Okay. What is it? When you put that answer, what is the name of it? Yes. So, can I see your stat crunch? Oh, no, look, okay, go ahead and open the data set again, just try again, and you can just, because your numbers are probably different. They're similar. I want you to work through the problem. See if you can answer the rest of them. Okay? Oh, okay. What about the second one? Is it paired or unpaired? It's paired. You're looking at the same thing, women, under two different conditions, right? So now, instead, you're going to use women light and women hard, right? And then go ahead and compute that. And again, you have to be careful with the language. They want to say how much longer is it going to take. So what should come first? The light or the hard? The light. It's going to take them longer to do the light under light strenuous exercise, right? Okay. Oops, I did a hypothesis test. Okay. 3.5, 21.5. I know, it's a little bit, yeah. Yeah, my staff on it. This one's tough, whether it's a two-tail or a one-tail.
So for this one, projected.
So in other words, okay, so that was a two-tailed test for that. What about C? Which of these is true? Individual times will be less variable. So what are we doing? We're comparing the averages with the individual times. In other words, they're saying, what if those numbers there weren't individual times? They were actually averages, okay? Which would be true? Would the individual times have less variation or more variation? But I'll ask it. So this is something that you were just talking about today. Will individuals have more or less variation? Right? Remember we gave you the question, sorry. Okay, so here's what they're saying. If you look at that data table, now what they're saying is rather than those times being individual times, those were actually averages. Okay? So will the individual times have more variation or less variation than the averages?
More.
They will have more. The individual will have more, right? And that's what the central limit theorem is telling us. The variation of x bar goes down with the sample size, right? So the individual times will be more variable, the standard error will be larger, resulting in a larger margin of error. So here's what you want to understand from this, okay? So what's happening is sigma is higher, so the standard error is equal to sigma divided by the square root of n. As sigma goes up, the standard error goes up, and the margin of error is equal to the standard error times the critical value. So this thing will go up. That's kind of the reasoning. Okay. So any questions on problem one? Everyone's pretty good? What do you think about problem two? Does anyone want to kind of offer an explanation for the hypothesis test? Besides Cassidy, I know she knows that. What would be the hypothesis test here? This one's actually a little ambiguous. If I was giving this on an exam, I would take one of two possibilities.
So it would be A. So you're saying the null would be that no, they're the exact same, and the other one would be like no, there actually is a difference between the two methods.
Right. So the way you think about this is you have two different ways to teach mathematics. You're looking at the average score of these two different ways. There's two possibilities. So one is that the new test could be better than the traditional. That's one possibility. The other is that there's a difference, okay? They don't say. And when they don't say, we tend to take a conservative, which is that they're different, okay? One thing that you should be aware of, all right? This is kind of important. When you're trying to figure out what type of hypothesis test, not equals, the words that you're usually going to see is difference or change. You're testing for a difference or a change. When it's a one-tailed test, in other words, you're testing to see if it's greater or less you're going to see words like less, greater, increase, etc. So you want to try to look at the words when they're talking about what it is they're trying to do in the study. Sometimes you have to get it from the context. So that thing about Bardo the baker, right? What were we testing for? In the first one we were seeing he was ripping off his customers. Well, what does ripping off his customers means? It means that the mean is going to be less than what he said it was, right? So sometimes in the context it's kind of implied, all right? But here we're going to take the conservative point of view. Okay. One thing you should always know, so if suppose you're on the exam and you just blank, you say, man, I don't remember anything, okay? One thing you should always know is that the equal sign always goes with the null. The equal sign is never down here, okay? And basically what would happen? If you had the equals, you'd be saying that nothing happened. It was the old thing, and that's all the alternative is saying. So you can automatically rule B out. Okay, so at least you have a 1 in 3 shot, right? All right. And now we can go ahead and do this. Is this a paired or an unpaired? Is this a paired T test? You have to be a little careful. So this is a situation where it could potentially be both. If you were testing the same student under 2 different conditions, that would be paired, right? But do we see any language like that? No. So we would assume it's unpaired. Okay, we're not saying that we're taking the same students, right?
I'm sorry to explain this. Why did you not equal to 0?
Okay, so first of all, it wouldn't be less than. We're not going to be testing to see if the new test is performing worse. I mean, that's when somebody makes a test, they're going to be testing to see if it's at least as good, right? And so this is a situation where there is some ambiguity. You could choose greater than, but really the conservative thing to do when we really don't know is to use non-equals. And it turns out, although we won't go into this, it turns out that it's harder to reject a 2-tailed test than it is a 1-tailed. So when people do 2-tailed tests and they reject a null, that's actually stronger proof that the null is not true, that something actually happened, okay? So this is a little up in the air. Does that answer your question though?
Yeah.
And to be honest, it's kind of poor wording. When there is that sort of ambiguity, they really should kind of put that in there. So, okay. And so now we just go ahead and compute the test statistic. How do we do that? StatCrunch, of course. All right. So let's see. We're going to go into StatCrunch, right? And whoops. How am I going to do it though? I don't have a data set. Summary. Good. Okay. So I'm going to go T-stats, toSample with summary, and now enter everything, okay? Does the order matter in this problem? No, because it's two-sided, right? So it doesn't matter who's on which side, okay? So now you just go ahead and enter the summary statistics. Oops, try to get them on the same page here. So 47.5, 31.8. Let me ask you a question. If you look at that table, what else tells you that it has to be unpaired? There's something that really screams that it's unpaired. What about this table tells you for a fact it has to be unpaired?
There's 2 separate. Or
the sample size is different. If it's paired, they have to have the same number. So that automatically puts that to bed, right? Because the sample sizes are different. Why? Because in a paired test, you're looking at the same sample under 2 different conditions. So the sample sizes have to be equal, right? So you automatically know. Okay, sample mean here is 3.9. Okay. So here we're testing that they are not equal, and we get the p-value. And of course, the test statistic is that thing t-stat, right? That's my test statistic. So I'm simply going to copy and paste that right there. That's my test statistic. And that's it. Okay. p-value is already in there, right? We just copy and paste it, 0.146. Oops. So if I have a p-value of 0.146, what am I going to do? Am I going to reject the null or fail to reject? 0.146. I'm going to fail to reject, right? Because the very biggest alpha can be is 0.1, right? So here I'm going to fail to reject. So now you have to be careful. Notice there's two different fail to rejects. So when we fail to reject, what do we say? Do we say there is evidence or there is not evidence?
There's not sufficient evidence to.
Right. Because this is the second quarter law. We say there's not sufficient evidence to find the person guilty. That's the alternative, right? So when we fail to reject, we say there is not sufficient evidence to believe the alternative, which is that using this new method, they have different means. If you look at this carefully, this is the alternative stated in words, right? The new method has a different mean than the traditional. That's the alternative stated in words. Be careful. Just because it says reject and there's not sufficient doesn't necessarily mean it's correct, because they could have been tricky and put the alternative down. I mean, put the null down here, right? And then that would have not been correct. So you have to be careful, all right? So we fail to reject, there's not sufficient evidence, and this has to be the alternative statement down here. Any questions on that? Okay. Let me see what the next one is. Fail to reject, there's not sufficient. Okay. This is a really good problem. So I'll tell you what, I think we'll stop here for today. I'm gonna stay if you guys want to work more, but this is a good problem to look at and think about. This question of paired and unpaired, sometimes it's not quite as easy as it seems. You have to think about it. Did everybody get a chance to sign the roll, by the way? Next week, we're just going to do regression all week. So if you want to get ahead, look at chapter 4, I think chapter 13.
I used to have this one.
No, you can do it now. Okay. Okay, got it. 19.
I live in the computer, I'm really funny for something.
Like some tough dudes. Oh, I'm sorry. That's seriously. I'm sorry. Well, I mean, yeah, so two things I would just mention. The first thing is that you do get to drop certain things just for those sorts of, contingency people get stuff happens, right? Like real life insurance. So there is that. On the other hand, also lots of things don't kind of go up. Right, feel free to ask if you need expansion or types of fine. But seriously, no, I don't think I'd be a little serious. I'd say this. Have you been checked out? Have you gone to the doctor though?
Yeah, they said it's like a possible since I can actually look at what is possible for it.
Right.
Just kind of like out of it. So obviously, not being looking at that, it's weird.
They say, you know, I got in a car accident last semester and I hit my head and the ERs came out and they said you didn't hit your head. I knew they did. There was a crack in my windshield and what happened was they didn't think it was because the crack was up here, my head was here. What was happening? I had the accident, my head was turning. And so I know I had it. But they told me, they said, when you have a concussion, your speech is slurred. They said something else, like you said, you can speak, you know, say your speech is slurred, something else. So they said you don't have any symptoms. It was like 15 minutes later, so you could go, okay. So I don't know what your situation was. If you,
I mean, like, it's like, it's dull, to that extent. So, I don't know.
I know the brain is hard, yeah, it's hard to explain what's going on. Yeah, keep me in the loop and whatever I can do to help. What's that? Adapt, improvise, overcome, right? So, yeah. All right. Well, I hope everything goes well.
I was here Tuesday, and I went there, and I didn't remember seeing it.
No, I didn't pass it on Tuesday. So I can pass it out. So if you want to sign, go ahead. Well, I gotta shut this down, by the way.